Yeah, first of all, let me thank the organizers to give me the opportunity to come back to Vienna and take part in this nice event. So I always learn a lot here and very much enjoy the talks. So what I want to speak about is a little bit off topic, but not so much today, probably. I think today we have more unitary representations in the program, so this fits sort of well. So the topic is covariant representations Hilbert Lie groups. We first of all explain the title a little bit. So what a Hilbert Lie group is so a Hilbert Lie group can be two things. One thing is you assume that the model space is a Hilbert space, but I want a little more. I want that the adjoint action is also isometric, which is sort of much more restrictive. So G will always be a connected Hilbert Lie group. And as I said, this means that the Lie algebra is a real Hilbert space. So is my writing big enough? Okay. Real Hilbert. And I want that the adjoint group is isometric. So this is an extra condition which somehow ties the Hilbert structure to the structure of the Lie algebra. So it's not just a differential geometric or functional analytic condition on the group. 1 minute. And then the goal is for these groups, so the idea, I should say, is if the Lie group is finite dimensional, these are the Lie groups with compact Lie algebra. Right? So whenever you have a compact Lie group, then you can sort of average, by averaging, find an isometric, make the adjoint action isometric by starting with some scalar product and then you average it. Or if it is semi-simple, you take the Cartan-Killing form. So these are the examples in finite dimensions. So the idea is these groups are the closest relatives to the compact groups. Closest relatives. Compact groups. And since it's so hard to systematically understand representations of infinite dimensional groups, it's good to start with the closest relatives to those which are rather simple to understand. So the goal is to understand active unitary representation I of T projective group Hilbert space. So this is the quotient of the unitary group by the multiples of the identity. This is the group that acts by symmetries in quantum mechanical systems. Right? So there you end up with projective representations, and in many situations you can lift them to unitary representations. That's again related to central extensions that was discussed in Cornelia's tutorial yesterday. Okay, so that's the goal. And you, of course, you can formulate this problem for general infinite dimensional groups, but one issue is that for infinite dimensional groups, you can typically not expect to classify all irreducible representations, so you have to approach the problem somehow from bottom to top. So you have to find good classes for which you can classify or specify classes which are more interesting than others in the sense that they really show up in quantum physics, terms of symmetries and so on. Okay. Now, what is a prototypical example? If you start with the Hilbert space, the little H, say H cases, K is set, and K is allowed to be the real numbers, complex numbers, or the quaternions. So I think of this as a Hilbert space over K in the sense that the natural scalar product is K valued, and then you have these three types. And for such a Hilbert space, you can say what Hilbert Schmidt operators are, or bounded operators. And bounded operators here means K-linear operators in this context. And find a trace, and those operators for which the trace is finite for A star A, these are the Hilbert Schmidt operators. Okay. Accordingly, you can specify a restricted or smaller unitary group just by intersecting the unitary group of this Hilbert space with 1 plus Hilbert Schmidt operators. And this becomes, in a natural way, a Lie group modeled on the intersection of Hilbert Schmidt operators with the Lie algebra of the unitary group. So this is the Hilbert Lie group. Lie algebra is what the 2 of H, the 2-Hermitian Hilbert Schmidt operator. The real scalar product on the space for which the group action is unitary. And one has to be a little careful here because I mean, the value of the trace would be real for the real numbers and the quaternions, and complex for the complex case. So one can take the real part of the trace of X star Y, and that would be an invariant in a product, turning this Lie algebra into a Hilbert space. So that's the prototype. And luckily, things don't get so much worse than what we see in the prototype, because there is a nice structure theorem from the 60s, I think 61, 62. And he analyzed, well, in a slightly different context, these Lie algebras by looking at sort of their complexifications, and he was looking at star structures on complex Banach Lie algebras called L-star algebras, E star. And what he proved is that if we have a Hilbert Lie algebra, then this is a direct sum, center, and simple ideals. One thing, and he also identified the simple ideals. So GJ could be either compact simple, so finite dimensional, or of this type, and that's it. Or U2 L2JK, where J is an infinite set. You see, if you have a finite set, this Lie algebra is not simple because it has a center. But if the Hilbert space is infinite dimensional, this Lie algebra becomes simple because the trace is not defined on Hilbert Schmidt operators. Right? base class operators from a dense subspace. So the commutator algebra is dense, and this makes it a simple algebra. So the main point in Schur's theory is to show that there are minimal ideals. I mean, what's clear in this context from the invariance of the form is whenever you have an ideal, then its orthogonal space is also an ideal. So whenever you have one, you get a decomposition. But then, of course, we want to go by transfinite induction, but then you have to show that there is a minimal non-zero ideal if you have a non-zero algebra, and that's the main point. And this is sort of Hilbert direct sum. Now, one important point in this description is that Hilbert Lie algebra is not determined by its simple ideals. It also carries the scalar product, right? So I did not say what the scalar product is, but it's clear that on every simple ideal, you have a one-parameter family of invariant scalar products, and depending on which scalar product you use, you get a different completion, at least if you have infinitely many summons. And this also plays an interesting role that you don't see in this kind of algebraic. Okay, so that's the starting point for the theory, say the algebra. And what I want to discuss next are so-called bounded representations. Bounded representations. So many aspects that I will use here have been nicely introduced by Milan. So it's not the first time you're exposed to these concepts. So bounded representation is basically a representation which is norm continuous. So these are the best behaved unitary representations, bounded if it's norm continuous. Okay, norm continuous means that on the unitary operators, you take the norm topology. On G, you have a topology because this is a topological group, and then you can ask for the norm continuous unitary representations. And for norm continuous representations, one has the key advantage that one can analyze them in terms of C-star algebras. I mean, Milan mentioned that infinite dimensional groups don't have C-star algebras. That's true, but sort of locally, whenever you have a representation of this type, you can look at the C-star algebra generated by the image, and then the representation decomposes in the same way as the corresponding C-star representation decomposes. So you have all the tools from the C-star world to analyze these representations. So one way to think about this is look at the derived operators, so the infinitesimal generators. On parameter groups, that these are all bounded operators. So you don't have to worry about complicated function analysis to study them. Now, how can we analyze representations of this type? I mean, the model situation are compact groups. So when you analyze representations of compact groups, you want a maximal torus. Well, and it's easy to get one. For example, in the Lie algebra, you can look at the maximal abelian subalgebra. That's something you can always try to find. And then in this context, one can also show that they are all conjugate under the full automorphism group, whatever this will be. So there is no no hard choice made here by fixing one. So that is corresponds to the Cartan. Okay, and then the replacement for a maximal torus. This, I mean, you could call it a maximal torus, but it's could be a little bit misleading depending on the context. So in any case, the exponential image of this subalgebra will always be of the form T modulo gamma, where gamma is sort of the kernel of the exponential function, so that's the discrete subgroup in this vector space T. And the typical torus situation is here you have Rn, and here you have the integer lattice, and then the quotient is a. Okay, now one thing that we learned from Schuh's theory is actually the way he obtained the decomposition into simple ideals is that he first looked at abelian subalgebras, and then if you have such an abelian subalgebras, you get a commutative family of bounded operators on a Hilbert space, and then you are sort of in business with spectral theory. But then the main point is to show in this context that the spectrum is discrete, that you really get a root decomposition of the Lie algebra, and once you have root spaces, it's easy to get the simple ideal. So what Schuh proved is that if you complexify, then we have a root decomposition of this type. Root decomposition. And again, this is sort of in the Hilbert space context, a direct sum. And well, once we have the root decomposition, we can specify co-roots. Roots. So these are the elements alpha check, or bracket spaces. So we know already what can happen. I mean, either this looks like in a compact Lie algebra or like in Hilbert Schmidt operators. So whenever you take a root space, take the corresponding negative, you generate a three-dimensional complex Lie algebra isomorphic to SL2C. So this space will be one-dimensional. So if I want to say what the co-root is, I only have to say what the value of the root is on this element. This is uniquely determined. Alpha of alpha check. One way to specify co-roots. And then important fact about the maximal torus is that if I look at 2 pi I times all the co-roots, this is contained in this lattice gamma that goes away when I look at the adjoint action, when I look at the exponential function of the torus. Okay, and this is important information on this group T hat, the sort of character group T. So the character group are the homomorphisms into the circle, and taking derivatives, I can think of this as sitting in the dual, sort of Hilbert dual of the Lie algebra, and there it's basically the functionals which take integral values on this lattice gamma. This or alpha, the values in gamma are something like that. I mean, we can always play around with 2 pi factors here, but much the point. Okay, so once you have this, you can already say something about the possible representations of T. And now these groups in the context of Banach spaces are also called toroidal groups because they look like tori. And they have a very subtle representation theory. I mean, these are infinite dimensional abelian groups, and one can construct Banach spaces and discrete subgroups in such a way that these groups have no unitary representations at all. Right? So they are really pathological things going on. But here, okay, we more or less know what's happening. But the first theorem I want to formulate here is about the abelian case. We are interested in bounded representations. So I want to say that, assume T is separable. And then I can say that the character group is countable if and only if all bounded representations T decompose into eigenspaces. This is an interesting fact that, I mean, you have to think about when you are analyzing the representations of these groups. So one thing is sort of easy modulo standard arguments. So if the character group is countable, and you have the C-star methods available for commutative C-star algebras, then you see that every bounded representation is coming from a spectral measure on this countable set. And if you have a measure on a countable set, it decomposes into atoms. And that's the decomposition of the representation. But the interesting issue here is that if this is uncountable, you can also construct measures without atoms, and then you see there are representations which don't decompose. Okay, and that's a good warm-up for the general, before I have to watch my time. For example of a...
T hat hat.
T hat.
I mean, Pontryagin duality in abelian cases. Can you save this?
Typically not. But for Hilbert spaces, for this is quite a shape. But I have to thought about that. I mean, there is a theory, I mean, already on the level of topological vector spaces. There it's about reflexivity, right? And then reflexivity is more or less meaning that the hat space is the same as the space. And on the level of Hilbert spaces, of course, the value is cool. But then the issue is also which topology do you put on the character group? And here I don't need a topology. I mean, think of this as endowed with topology of pointwise convergence or the corresponding.
Is there a Hilbert Lie group structure T hat? Or you could restrict T hat.
Like, I mean, if it's countable, it's discrete. So I think of this as a discrete group. But then you see if you have a discrete group and you do the usual thing, you create a compact group on the other side. So then you would end up with a sort of compactification of T as T hat. Yeah, I mean, I don't know, but this is an issue that people are using abstract function analysis. But I wanted to show you an example to understand where this comes from. So one example is that if you look at L2, say over the natural numbers with values in R as a Hilbert space, and you look at sort of the integer valued elements. Right? So these are sequences with integer values, which are little L2, so they are only allowed to have finitely many non-zero entries. So this is like the free group generated by the basis, and then he had is countable. I mean, basically, it's this group, dual side. Now, to get an example where this is non-countable, you can also take the same Hilbert space. All separable Hilbert spaces look like this anyway. And then you can look at the subgroup generated by the sort of scaled up basis vectors. And if you have larger vectors, it's easier to have integral values on them. So you get a larger character group. And in this case, T hat is uncountable. And this is because now you're allowed to have infinitely many entries. And then you have sort of binary sequences in there, so you get an uncountable set. And once you have Cantor sets, they support non-discrete measures. On here. Okay. Now, the theorem that I wanted to mention about bounded representations is that we assume
and weakly closed subgroup. Weakly closed have Hausdorff dimension 1, which is completely strange. Yes.
Okay. So let us assume that the center is separable and has sort of countable character group. Then we can, well, we also want to assume that the set of co-roots is bounded. You see here in this example, you already get the flavor of this. So what you mod out is something like the co-roots. Right? And if you have a bounded set of generators for the co-roots, things are nice. But if you have large co-roots generating the thing, then things get ugly. So if I assume that the set of co-roots is bounded, then everything is nice. So for example, bounded representations are direct sums of irreducible ones. And of course, then you ask how the irreducibles look like. Reducible representations. Well, they factor through finitely many summons in this decomposition. So they come from finitely many simple ideals. Quotients. That's finitely many simple ideals. And they are like to call extremal weight representations. And what this is, I explain in the next. What are extremal weight representations? Well, in a way, it's something like highest weight representations without saying what highest means. Right? Because to say what highest weight representations means, you have to choose a positive system of roots, but when you have infinite dimensional root systems, there are so many positive systems that that's hard to specify. So what we need to deal with them is, first of all, the maximal torus. And then we also have the Y group, which is the normalizer of the torus, which contains the torus as well. And then I divide out what does nothing on the torus. Of the while group. And I can say that pi is an extremal weight representation if following is true. I want that the restriction of pi on t is discrete. And we have already seen here that if the character group is countable, this is always the case, right? So that's part of the structural context. And if this is discrete, it decomposes into eigenspaces of the torus. So I can look at the corresponding weights sitting in the character group, which I think of embedded in the dual space. So this is the weight set of representation on T. And the extremal weight condition is that this should contain an extreme point, but this is a discrete set. So we want that there exists a lambda such that this is contained in the convex hull of the while group orbit. The picture is like this. SU3, you have these pictures. So this could be a weight set, and then the extremal weights are like this. So this means that the whole weight set is contained in the convex hull of the while group orbit, and then one can also show that all extreme points lie actually in this orbit and all that. And in this sense, one can classify these irreducible bounded representations, and the classification is sort of easy in a sense. So if you have two such extremal weight representations, they are equivalent if and only if U is contained in the while group orbit of lambda. So your parameter space is the set of weights of the maximal torus modulo the while group action. And in finite dimensional compact groups, then you have the dominant weights, and they produce canonical representatives, and then you take just these. And in general, you don't have a canonical positive system. You have to do it this way. So typical example in our prototype, if G is 2 of J, then the torus is the group of diagonal elements, and here this is sort of the corresponding L2 space, and the gamma, I should say the T hat, the characters are basically the L2 functions with values in Z. So again, this is the P group on K generators. And then the Y group here is isomorphic to the symmetric group of finite permutations. So not the full group of bijections. So this is only the finite permutations. And the parameter space is then T hat modulo this group. So this is a huge space, even if you have sort of only finite support. You can sort of, it makes no longer sense to order these highest weights because there is no order on the index set. Or there are many orders, you can do this for many orders, but this is what it is. I mean, sort of easily understand how this classification works. Okay, so time is flying. Let's see. I mean, one thing one can also say here, you see, this is about the good context, right? So if the co-roots are bounded, then all representations are nice. We know what they are, basically. Now, there's also converse, which says that if the set of co-roots is unbounded, then there are factor representations of type 2 and 3. So this is sort of the dark side of the theory, where you have to use completely different tools to understand what is going on. And I mean, there the picture is much less complete. But it's clear where the boundary is. I mean, it's the boundedness of the co-roots that decides on whether the theory is nice or not. Okay, so I don't want to go too deep into that. I want to show you some of the interesting tools that come up in this context, and they are related to automorphisms. Now, the idea, if one goes beyond bounded representations, is one wants to somehow implement regularity conditions. And one way of a regularity condition, well, this is something one learns from operator algebras or physics, is to impose one-parameter groups of automorphisms with nice properties, like covariance properties for automorphism groups. And for that, let me stick to this prototype situation where H is an infinite dimensional complex Hilbert space. So we are now dealing with a simple Hilbert Lie group. Now, in this case, one can easily say what the automorphism group is. So its identity component is precisely the projective unitary group. And well, the group has two connected components because you have something like complex conjugation on this space, so you get two components. So this means that every automorphism is induced by a unitary operator. So to get one-parameter groups of automorphisms, well, I have to look at unitary one-parameter groups. They can be written form where A is a self-adjoint operator. So this is Stone's theorem. This tells us that one-parameter groups, unitary one-parameter groups have this form. So this could be unbounded. And what I mean by covariant representations is basically we look at this group G alpha, which is the semi-direct product. So we enlarge it, and covariant representations are representations of the groups G alpha. So I want to impose some regularity condition by prescribing a one-parameter group, and then I want that the whole representation has some covariance in the sense that I can extend it. Now, self-adjoint operators are very complicated objects, and the interesting point here is that these groups are no longer Lie groups if A is unbounded. So what I always get is a one-parameter group of automorphisms which defines a continuous action of R on G. So this is always a topological group. It's a Lie group if A is a bounded operator, but in general it's only so-called half Lie group. So it's a Banach manifold. You see it's G times R as a manifold. But the group operation may not be smooth, and the critical part is multiply from the right with elements of G, because then you have to get past the one-parameter group. So the left multiplications are C infinity. This is called a half Lie group. And in this context, this is a very useful thing. And the key point is these half Lie groups, I mean, they look so harmless, but they have interesting facets to their theory. One is that the tangent space in the identity, this is what you see from the manifold structure. So the tangent space, maybe I should write it like this. I mean, the tangent space is not a Lie algebra, right? Because you have this unbounded operator, so there is no Lie bracket. But it's this, and this is still the same as the space of C1 one-parameter groups. The interesting point is still tangent vectors generate C1 one-parameter groups. And this is a very interesting thing and not obvious. I mean, it's clear that if you have a C1 one-parameter group, you can differentiate at the identity and get a vector, but the other way is not clear. So this is in a paper I wrote with Timothy Marquis some time ago. There's also a nice paper by Peter Mischa and collaborators on half-D groups. So why is this interesting in our context? Well, first of all, the interesting one-parameter groups coming from physics never have bounded generators, right? So you have to face this problem that you have to deal with non-differentiable actions. Now, but there is a beautiful theorem which goes back to Weil and von Neumann. And this is really a kind of von Neumann thing. I mean, what Weil proved in the context of bounded integral operators was that you can also always find a small perturbation of the operator that makes it discrete. So when you study integral operators, you want to calculate eigenvalues, etc. But if the operator has continuous spectrum, you don't know what to do. So what they proved is if you have a self-adjoint operator, then you can write it as a sum, E plus, for the other one, T, with the self-adjoint diagonal, and T self-adjoint Hilbert Schmidt operator with norm arbitrarily small. This is really a theorem you would not think about. I mean, me not. Because the point is they don't commute, right? So this is not spectral theory. It's really hands-on kind of manipulation. But this is the perfect environment for our context when we deal with groups of Hilbert Schmidt operators, because the T's, they produce inner derivations. So if we look at this decomposition here, we can reduce to the diagonal context. And the result is that we write alpha dt E, so these are diagonal operators. And when I say diagonal, I mean for some given orthonormal basis, then this group G alpha is the same, or isomorphic, as the corresponding group I get from the diagonal one-parameter group. And this is an isomorphism of half-Lie groups, a C1 isomorphism of this context. So half-Lie isomorphism. Right? And then if I'm interested in covariant representations, I want to study representations of this group. Now with this Weil von Neumann decomposition, I'm reduced to diagonal automorphism groups. And this is much nicer because the diagonal automorphism groups are compatible with the maximal torus. Right? So this produces a reduction to the case where A is equal to D. So this means that alpha t, well, fixes t pointwise. And this is nice because now one can sort of, in this context, try to develop the sort of representation theory in the way, in the spirit of compact groups. So you have to understand what happens on the diagonal and then see how you can extend. When did we start? Did we start in 10? Okay, so I don't have much time to. Okay, so maybe. To this one. Yeah, so I have to say what semi-bounded representations are. So bounded representations were representations where all the infinitesimal generators, we have them here, right? Where these are bounded operators. Now, to say that the representation is semi-bounded means that we have a large supply of operators of this type, which are semi-bounded if you multiply them with I. And this you can say as follows. What pi is semi-bounded if the following functions, so s pi of x, primum I d pi of x. So this will be a self-adjoint operator. So this supremum will have values in R or could be infinity. If this function is bounded in some open subset. Of T. And well, if you take this as semi-bounded and then you see if this open subset contains 0, then this implies that all these operators will have to be bounded. And these are just the bounded representation. And this leaves the possibility of having something like an open convex cone, which does not contain 0 because it is open. So this is a very strong form of the positive energy condition. And then maybe I cut this short by saying that if we have Hilbert Lie groups, semi-bounded implies bounded. So this means that weakening this semi-boundedness, this boundedness condition to semi-boundedness does not give any more representations, and that's interesting consequence of fixed-point theorems. But from the perspective of representations, this is a little bit disappointing. So one has to do something else to find more. The idea is you first look at slightly smaller group and then study how things could extend. We call it the extension theorem. Again, H is L2J. G is the corresponding simple Hilbert Lie group, and I also want an integral function on this index set, but now I assume that this is only bounded. So we know already the finite support functionals, they appear for the norm continuous representations. So now we want to go beyond and look at least bounded ones. And for that, we can say that exists a bounded prima weight representation. Lambda of Well, we know it cannot exist for U2, but it exists for U1. So this is a unitary group intersected with 1 plus trace class. So that's a smaller group. Now on the Lie algebra level, we have trace class operators, and on the diagonal, we have little L1, the dual space is L infinity. So these functionals define candidates for highest rates in this context. Right? So we have this representation. And then we can say, if we look at this diagonal operator, that we get from lambda, diagonal operator, and consider the corresponding one parameter group. Then this pi lambda extends to a covariant representation alpha, but one can even say much more. One can say to which sort of maximal group it extends. It even extends to res HD. These are the unitary operators. The property that if you conjugate this D, so this diagonal operator, and look at the difference, if this should be Hilbert Schmidt. That's a typical restricted restriction condition one finds there. Then this is the maximal group to which pi lambda extends, but only as a projective representation. So what one loses by the extension is no smoothness or whatever, but one loses the sort of multiplicativity. One has to go to the projective representation, and this means effectively to get a unitary representation, we need a central extension. And if you want to see the corresponding co-cycle, omega, easy to guess. So that's something like the trace of D is the bracket. That's the kind of co-cycle you expect. So here we have brackets of Hilbert Schmidt. So this is trace class times bounded operator produces. Okay, so my time is up. I think I stop here.